Now it is my pleasure to introduce our next speaker, Vladimir Vovk. He's going to talk to us about calibrating prediction uncertainty with validity guarantees. Mostly an introduction with a little bit of not so introductory. So please go ahead.
Thank you. Okay, so my emphasis will be on validity guarantees, what we can mean by validity. So it's very closely related to what Johanna called calibration, and what is usually called calibration. So calibration is one side of validity. So let me first talk about my plan in general for this talk. So please feel free to interrupt me. So if I'm moving too fast, for example. I will talk about randomness. First, a terminological remark. So I will use it in some old-fashioned sense, just meaning that I assume ID data. So randomness is just ID in this, for the duration of this talk. And I will concentrate on what happens under the assumption of randomness. There have been lots of generalizations of these ideas to beyond randomness, like to time series, to time series, dataset shift, but I will talk about randomness. So first, two methods that I know that have guaranteed validity under randomness are conformal prediction and event prediction. So I will review them very, very briefly, concentrating on the intuition behind them. I will try to not to use some too dense notation. Okay, so usually we're interested in validity and efficiency of our prediction algorithms, or calibration and sharpness in a different terminology. So in the last part I will talk about efficiency as well, but mainly it will be about validity. So my last part will be if there are other ways to achieve validity under the assumption of randomness. It will be my last section, but let me start from conformal prediction. So first, it's different from Bayesian prediction. So of course, the dominant approach to uncertainty quantification is Bayesian. So it's perfectly valid, perfectly efficient, but under strong assumption. We just assume that we know we have a full probabilistic model for our data, for the way our data is generated. And then, once we know this, we can be perfectly valid, perfectly efficient. But now I will be talking about relaxing this under randomness. And of course, you can do much, much less if you have this weak assumption, which is still very, very strong. But it's weaker than just assuming you know the probabilistic model. So first, my terminology. So things in red, it's the terms I'm using. So we have some training sequence. So it's a toy problem. So you have a training sequence Z1, Zn of size n, which is fixed. And we have a new object. So each observation Z consists of two parts, x and y. And we are trying to label an unknown x. So a new x arrives, this xn plus 1, xn plus 1 arrives, and we want to predict its label, yn plus 1. Sometimes I will be using object space, label space, and observation space, the Cartesian product, the space where the observations are taken from. So they are measurable spaces. I will not mention measurability. Everything in this talk is measurable. Okay, so let me define conformal prediction first. So we start from a non-conformity measure. So a non-conformity measure is a function that takes as an input some bag of observations or multi-set of observation, unordered set, unordered sequence, and another observation z in this bag, and it assigns a non-conformity score to it. It can be any function, but the idea is that the non-conformity score should somehow reflect how strange z is in this bag. There are lots of ways to define it. One way is just you can train some prediction algorithm on this bag of data. This prediction algorithm will output some prediction for the test object. Let me call the z my test observation. So I'm trying to measure how strange it is. So I can just subtract this predicted observation y hat from the rest, from this found from this bag. I subtract it from the true label and take it in absolute value. Okay, so it's one way to define the strangeness of this observation z. So once I have this measure, we can compute the conformal p-value. So this, of course, when you have this non-conformity score, this strangeness measure, we don't know its units. Is it miles? Is it meters? So now we want to normalize it somehow. And the way we normalize it, if we compute this p-value, we find the rank of our test observation. So we have our test object, and we are trying each possible label for it in turn. So we postulate some label y, and we form an augmented training set, the z1 to zn, and we add to it the test object plus this postulated label. We try all possible labels. And for each possible labels, we are trying to figure out how strange it is. So what we do, we take the rank of this, of the test observation in our augmented training set. The rank is, so it's 1 for the strangest observation in the bag, 2 for the second strangest, and so on. We take the rank and we divide by the size of the augmented training set, n plus 1. So we get a p-value. And it's really a p-value under the assumption of randomness. Not even under the assumption of randomness. You can see the ranks, you expect them to be distributed uniformly. So unless you have some ties, for example. And then the p-value, it will be also distributed approximately uniformly, if n is big. So it will be a p-value between 0 and 1. So it's a normalized non-conformity score. So it's the way of normalizing it. Okay, so this is how conformal prediction works. So it's a primitive idea. But what is important here, we can only assume that our data are exchangeable. We don't need randomness. We need less. So the ranks are also expected to be uniformly distributed under exchangeability. And it will be important later, because exchangeability is different from randomness for finite sequences. For infinite sequences, the difference is tiny. It's non-existent, almost. Okay, so you can regard this function that maps each possible label y to this p-value p of y. You can regard it as our prediction function. So it's the full prediction for the next label. For example, can you be okay? So you can make a confident prediction if this p is small everywhere apart from one label, where it is not small. Then you can confidently predict that label. So here you have this prediction function. So it's an example of a p-value function. So in statistics, several people have been promoting the use, a wider use of p-value functions. So this is an example of that. So it's like a fuzzy predictor. So it outputs a number between 0 and 1. If it's very small, it means this label is unlikely to be the true label. You can create a crisp prediction set from it. So if you choose some significance level epsilon, so it's our target probability of error. And then you form a prediction set. So the prediction set gamma epsilon, you just include into it all y's which are not rejected at level epsilon by this p-value function, for which you take only y's for which the p-value is more than epsilon. And then since p is a bona fide p-variable, I will say p-variable in such cases, so the definition is that a p-variable must be epsilon or less with probability at most epsilon. So I will use p-variables repeatedly in this talk, and of course everything happens under the assumption of randomness. So it immediately implies that the probability that gamma epsilon makes an error, when I say makes an error, I mean it fails to cover the true label. So the probability of this doesn't exceed epsilon. Okay, so it's the way conformal prediction works, and it's automatically valid, meaning that the probability, you can control the probability of error. But what you want to achieve, you want predictive efficiency. You want two kinds of efficiency, at least. You want predictive efficiency, you want these prediction sets to be as small as possible. Of course, you can always say everything is possible and then your probability of error is 0. It's not interesting, it's not efficient. So you want gamma epsilon to be as small as possible, or you want this prediction function to be as small as possible. It's equivalent. But you also want to have computational efficiency. So what is computational? How can you achieve computational efficiency? So in principle, this method is extremely inefficient unless you can do some computations on paper. Unless, for example, your y hat that I mentioned before, that you use in computing your nonconformity score, it's coming from least squares, or the lasso, or ridge regression, something very well behaved. In this case, you can do calculations on paper. But if it's something like neural nets, in this case, remember, for each postulated label y, you have to compute those nonconformity score, and you have to do it from scratch. Because when you change y, this postulated label, all nonconformity scores can change. So it's a lot of calculation. If you have a big test set, and you process each test observation, each test object separately, then you have lots of calculations, and you have, especially if your label space is big. So what people often do, you can use inductive or split conformal prediction. It's the same thing. So what you can do, you can take your training sequence of size n, and you divide it, you split it into two parts. Training sequence proper and a calibration sequence. Then you find some predictor from this calibration sequence proper, you train your prediction algorithm, and then you can find very efficiently, you can compute the p-value from the calibration set. So this is the way, so here I don't define it formally, but this is the idea. It's very easy to implement, it's very natural. So you can also, this way you can achieve computational efficiency. But of course, prediction sets or p-values are not, in many cases, they are not enough. We want to have probability predictions, to have probability distributions. For example, if we are interested in decision making, if we have a probability distribution, we can find an optimal decision. So here, how can you get probabilities from these p-values? Of course, we all know statisticians like telling us that p-values are not probabilities. But they almost become probabilities if you impose some discipline on them. Okay, so how, and sometimes you can do that. But before I do that, let me redefine p-values. Let me make this property of validity slightly stronger. So when you have a tie, when you consider, consider some alpha I, some nonconformity score in your augmented training set, when you compare it to the nonconformity score for the test observation, then before I have alpha I is greater than or equal to alpha n plus 1. When you compute the rank, we didn't break when we have a tie, we just counted as it fully this alpha. We just counted the number of alpha I greater than or equal to alpha n plus 1. Now we want to be more careful, and we include some randomization. Many people don't like it, but still, theoretically, it's something valuable. So what we can do, we take some TOR, some randomly generated numbers from 0 to 1, something coming from random numbers generator. And when alpha I is equal to alpha n plus 1, we multiply the number of such alphas by 2. There will be at least one I here, because I is allowed to be n plus 1. So it's at least 1. But if it's exactly 1, then randomization almost doesn't matter. It's something tiny when n is big and we don't have ties. Then it's just 1 over n plus 1. You multiply it by 2. But after this step, you can say that now this p-value, it's uniformly distributed between 0 and 1. So it's an exact p-value. It's exactly uniformly distributed. Okay, and after that, it turns out that for many algorithms, what you can do, so for example, you can define your alpha nonconformity score as y minus y hat in the old context, but without taking the absolute value. In this case, this p-value is a function of your label. It will be increasing, and you can make it increasing from 0 to 1. It becomes a cumulative distribution function. So we can use it for prediction. In this situation of regression, by regression I mean y is equal to the real line. The labels are real numbers. Okay, so if you achieve this somehow, you can do it for ridge regression, for example, for some nice underlying algorithm. Or if you use inductive conformal prediction, it's much easier to achieve. You can use lots of different algorithms. So let me show what it might look like for a tiny training set. So you will have you will get a prediction function. So what I have here, so this random number 2, I allow it to vary from 0 to 1. So at each y, on the horizontal axis you have y. The value at each y will be an interval from τ equal to 0 to τ equal to 1. So it will be a distribution function. It will look like a distribution function, but it's thick. So like for ridge regression, its thickness will be 1 divided by n plus 1. It will not be very thick. Okay, so this is what you will get. And what is interesting here is that this property that p-value is uniformly distributed between 0 and 1. It becomes exactly calibration in probability. So Johanna mentioned it in the previous talk, so it's a standard notion of calibration in probability forecasting. Many people worked on it, so you get it for free. And there is, so I call it here Gnating et al.'s paradigm. So Johanna also mentioned it in her talk. So here our idea is to maximize the sharpness of our predictive distribution subject to calibration. Calibration, we have some kind of calibration here for free. And we want to maximize sharpness. So what is sharpness? Calibration, so you know what it is the uniform distribution of this p-value function at the actual label. So it's uniformly distributed. You know it's always true under the assumption of randomness. So sharpness is a property of predictions only. So calibration depends on both predictions and actual labels. Sharpness is just about the predictions. You want your predictions to be as concentrated as possible. You want your calibration function not to be spread out, but to just to go up sharply. Or the PDF, the density, you want it to be as concentrated as possible. So it doesn't depend on the actual labels at all. So here we have, for conformal predictive systems, we have calibration automatically, and now you just need to achieve sharpness, which is difficult, of course, and it's our real goal, so it's not easy. Okay, so now let me talk briefly about using a different an alternative to p-values. So p-values have been criticized recently, so people say they're too complicated. There are lots of objections against those. And e-values as alternative to p-values are becoming popular in statistics. Not many people are working on them, but more and more. So let me talk about conformal e-prediction. How you can replace p-values by e-values. So e-values, they are sometimes considered to be a middle ground between p-values and Bayes factors. So it's some move towards Bayesian statistics. So for p-values, I mentioned how they are defined. So it's for each threshold epsilon, we have some requirement. For e-values, the requirement is more global. We require an e-variable, a variable for producing e-values. We want its expectation to be 1 or less. So it's a more, you don't have any threshold, it's a global requirement. Okay, so how can you get e-values using these ideas of conformal prediction? So here again, we have some nonconformity measures, but now I call it nonconformity e-measure. So the way we do it now, when we have a bag of observations, for each element, to each element of this bag, we assign some nonconformity score in such a way that the average of these nonconformity scores over the whole bag, it doesn't exceed 1. Okay, so it's some requirement for each bag. And then this requirement will imply some global requirement that a similar requirement, but at a different level for conformal predictors. Let me define them now. First, how can you get these nonconformity e-measures? Suppose you have some way of producing alphas, but it's not normalized. You can always normalize it, of course. A small step, you can define alpha or some function of alpha by the sum of all alphas. No, sorry, it will not work. You should take the average. You should divide it by the average. Okay, so it's a type. I will correct it. So now the definition is it's very simple of conformal e-predictors. So the way you find this prediction function, so now we can call it an e-value function. So for each possible label y, for your test object, what you can do, you can again create this augmented training set. And your prediction will be just the nonconformity score assigned to this test object. It's enough. So this is a conformal e-predictor, and you can use this prediction function for prediction. Again, as usual, you can form a prediction set. So now you take some, as your significance level, you take alpha. Typically, it's a big number. So e-values and p-values, they work in opposite directions. So when a p-value is small, then you can reject your null hypothesis. It looks suspicious. For e-values, when an e-value is large, it means you can reject your null hypothesis. It looks suspicious. So here what we do in our prediction set, we include only y's for which the e-value is below some threshold alpha. So for example, Harold Jeffries had some thresholds for e-values. So he was talking, of course, he was not talking about e-values, he was talking about base factors, without calling them base factors in his book. But still, these thresholds, they are applicable as well to e-values in general. What he had is some special case of e-values. So he had the square root of 10, 10, 10 to the power 1.5, and 100. So here you take some alpha, like 10, for example, and you form this prediction set. Okay, so you can also get these prediction sets. And you also, but the notion of validity becomes slightly more complicated. So now, of course, it's still true. You can apply Markov's inequality, and now we can say that the value of this prediction function at the true label is an E variable. So it's the expectation of it under the assumption of randomness is 1 or less. So it's a bona fide E value. And since the expectation of this, of E of y n plus 1 doesn't exceed 1, you can say, you can have a property of validity for gamma alpha. The probability that gamma alpha makes a mistake in the same sense, fails to cover the true label. It never exceeds 1 over alpha. So if alpha is 100, it never exceeds 1%. But of course, this property of validity, it's very, very weak. Our property, our original property of validity is stronger when we say that the expected value of E of y n plus 1 doesn't exceed 1. It's stronger, but we can still rephrase it in terms of the probability of error for gamma alpha. But now we should say that the probability that gamma alpha makes a mistake integrates to at most 1 over all alphas. So it's not about 1 alpha. It's a cumulative property. It's a property for these prediction sets overall, not about just one of those prediction sets. Okay, so it's very briefly introduction to conformal E prediction. Why do you want it? Why is it? It turns out that conformal E prediction has some advantages over conformal prediction and vice versa. So none of these dominate each other. So first, if you're interested in conditional conformal E predictors, meaning that you want to have validity, but not marginal validity, overall probability of error, but you want it to be conditional on your test objects. There are lots of many different kinds of conditionality, and an important kind is what is sometimes called, you want it to be object conditional. Conditional on the object, on your test object, or some features of the test object. And it's much, much easier to design conditional conformal E predictors. So I will not go into the details, just I will claim this is an advantage. Another advantage is that you can implement an idea of so-called cross-conformal prediction, so I didn't mention it. But what you can do, so when you use inductive conformal prediction, you have a split of your training data into two parts. One part is used for training only, and the other part is used for computing the p-values or e-values. And it's very inefficient, so you lose in your predictive efficiency. So you can use the idea something like cross-validation. You have your training set and you divide it into folds. And then each fold is used in turn as a calibration set. So you can implement it for conformal prediction, you get cross-conformal predictors, but the problem with them is that they are valid in practice. You will get perfect calibration lines, but they are not perfect in theory, and even in practice, in computational experiments, when you do lots of randomization, you can break validity. For conformal E-prediction, when you implement this idea of cross-conformal E-predictor, you can't break it. You have a provable validity. It's just because the average of E-values is always an E-value. For P-values, it's very difficult to merge P-values. How do you do that in general? But for E-values, a very good method of merging is trivial. You just average those. Okay, so this is why it's another advantage, but also conformal prediction has important advantages over conformal E-prediction. So like its property of validity is much simpler. You just say you make a mistake with probability epsilon or less. So what can be simpler? For conformal E-prediction, it's slightly more complicated, if you don't want it to be too weak. Conformal predictive distributions, in terms of E-values, they don't exist. And also, conformal E-prediction allows you to test the assumption of randomness, which you can't do using conformal E-prediction. Okay, so that's all for conformal prediction. If there are no questions about it, yes?
I think I missed something right at the beginning. You did talk about this splitting the training set into, or the initial set into a training set and the set for calculating the performance impact. But you also suggested that you didn't have to do that, and that was the impression I got. And if you don't do that, then aren't you going to have a problem of overfitting, so that
okay. Just to understand what you are saying, are you talking about what is sometimes called full conformal prediction, this formula for p-values, when you don't have a split? Or is it about cross-conformal prediction?
Okay, so at the beginning of your talk,
yes.
So before you got into the more complicated stuff, so marginal...
Yes, yes.
Right. So you're going to train your prediction algorithm on a particular set of data.
Sure.
And then you're going to use that same set of data.
That's right. Yes. Yeah.
It just seems to me that if you do that, you're going to have an overfitting problem.
Okay, yes, that's clear. No, you don't have overfitting, and the reason why you don't have overfitting is that you consider each y in turn, each possible label in turn. When you have y, it's possible that your original algorithm will overfit. The one you are using, if you are to use my example, alpha is y minus y hat. It's possible y hat will be badly overfit. Of course, it's possible. But then this conformal machine will fix it, meaning maybe your prediction set will be very bad because of this overfitting. But what you do, you try each y in turn, and when you overfit it to each y, and then the nonconformity score for each training observation will change a lot. It will completely mess up this whole picture. And your prediction set will become very large. So yes, you overfit, but you pay for it, and it becomes visible. You can see you overfit your data.
So your interval just becomes wider.
That's right, if you overfit. Yes.
Thank you very much.
It's a matter of efficiency. Of course, for efficiency, you don't want to overfit. Okay, yes?
I'll start. I think you define this for like a deterministic algorithm that makes a prediction. What happens if your prediction method gives you a probabilistic distribution into a version of conformal prediction in that case?
Okay, so if it's a probabilistic prediction, so one way, so we can still use the same method. So when you compute the nonconformity score of some observation, you will have two parts, x and y. From x, you compute this probability distribution, and then you have y. This, you know what the label is of this training observation, if it is a training observation. So we can use, for example, the value of your function on this label. And what you get in the end, when it's a conformal predictive distribution, you will get in the end, it's likely to look similar to what you started from. If you didn't have any bad overfitting, so if your algorithm was very good, maybe it will completely change it. But if it was a good algorithm, if your initial prediction was reasonable, So in many cases, which it has been done, in many cases you can show that your conformal output will not be very different from what you start from. So if your initial prediction is Bayesian, for example, or initial probability distribution is Bayesian, and your Bayesian assumptions are satisfied, it's a research program which in our book we call it Bournaev-Wasserman program. These are people who told me about this idea. So the goal here, of course, your conformal predictive distribution cannot be better than what you started from. If what you started from is ideal, but it will not be much worse. It will be about the same. Okay, so let me talk now about Venn prediction. So it turns out Venn prediction it's another method of prediction, but it works only in the case of not in the case of regression, but in the case of classification, when you have a small number of possible labels, like 2 possible labels, for example, in the case of classification. And what it achieves is what Johanna called auto-calibration. I call it slightly something different, but it's a stronger notion of calibration. So with some idea, it's called Venn prediction because it follows John Vance, some ancient book by John Vance, who's a Cambridge probabilist. And it's a straightforward implementation of his frequencies definition of probability. So it's all about frequencies, observed frequencies in your training sequence. So we start from a Venn taxonomy. So a Venn taxonomy means you have a bag of observations and you split it into some sub-bags, some categories. I call it categories. Okay, so or equivalently, you have this bag and you have some equivalence relation on this bag. And then we are interested in equivalence classes. So I will give you some examples. So like the population can be the population of England, and the bag can be, I don't know, men and women, or people classified into different ages. Okay, so we start from a taxonomy. And now, how do we do Venn prediction? So we are given this training bag, our training observations, and we don't need, there is no dependence on the order. So this is my notation for a bag. It looks like a bag. So again, as in conformal prediction, we try each potential label y in turn. And for each y, we apply this Venn taxonomy. So py, so for a potential label y, we compute py. So we just find, we have this postulated label y for xn plus 1. We divide our augmented training set into bags. And of course, this division, it will depend in principle on y. So we do it from scratch for each y. And you compute, so you find the category of this test observation, and you just report the empirical frequencies in this bag, the empirical probability distribution in this category to which the test observation belongs. So typically, you assume that if you don't have lots of overfitting, you assume that different py's for different y's will be close to each other. And in this case, you get something like imprecise probabilistic prediction for the label of your test object. And if they are not close to each other, then it will be obvious. You will see they are very different. Maybe you are overfitting, you don't get probabilistic prediction. So now you can also define a notion of calibration. So let's say that a random element taking values in this set P of y, as my notation, I think it's standard in some books at least. So these are all probability measures on the label space y. So it's our probabilistic prediction. So it's perfectly calibrated or auto-calibrated for our for the label, which is a random label y. If the probability that this random element is y, some element given p, given this, so it will be the prediction in applications. It will be the value of p on this one element set, y. Okay, so then we say it's perfectly calibrated, and we can just formalize in a very primitive way. Maybe there are better ways of formalizing it. But it's clear that what we are doing, it's unbiased, because we go over all possible y's, and then we just report frequencies in the category. It seems it must be well calibrated. But how do we formalize it? So a simple way is to define a selector as a function, a random variable that maps the whole data set, including the test observation with its true label. It maps it into a label. And then the simple property of validity is to say that for some calibrator PS, so we take just one element in this multi-probability prediction. So when predictors output a multi-probability predictor consisting of several probability distributions. So there is a selector such that PS will be perfectly calibrated, auto-calibrated for yn plus 1. And it's clear what this selector should be. It should be the true label. Okay, so we have this notion of perfect calibration, not for the whole multi-probability prediction, but for one of its elements. And if all elements are close to each other, then it's good enough. Okay, so any questions about this? So it's just very briefly the idea of Venn prediction. So here I just given Venn's example. So philosophers discussed this problem of the reference class, what I called Venn taxonomy here, at length. And I think this expression, problem of the reference class, it was coined by Reichenbach. And Reichenbach thought that you should use as your category the smallest class for which reliable statistics can be compiled. Okay, but now let me tell you how you can use this Venn taxonomy. It's a big problem, how you can define it. And there is, in the binary case, when your label space is binary 0 or 1, there is a very, very natural way to do it. I don't know how to do it in general. But in the binary case for binary classification, you can do it. So the idea here is that we call it Venn Abus prediction, because it's based on this power procedure. I think somebody already mentioned it in the previous talk. I call it procedure, so the last A is algorithm. It's what? Full adjacent violators algorithm. So algorithm is already here. So this procedure gives you a very natural Venn taxonomy. So how does it work? So what you can do, suppose you are given a bag of observations, and you want to compute this Venn taxonomy. So what you do, you can train some machine learning algorithm, for example, some scoring algorithm. And this scoring algorithm, for each x, for each object x, it gives you a score, which means which is intended to be the tendency of this x to be labeled as y. It can be, for example, the probability of y computed by this algorithm, but it doesn't have to be calibrated in any sense. So it's just some score. And now we want to turn these scores into a Venn taxonomy. How do we do it? So now we plot. We take this back and we plot Sx versus the true label. So here we have the scores. And then for each score, we have the true label, 0 or 1. So typically, first you will have zeros and then ones. So this is what you expect. But of course, it will not be monotonic. So what people do in such cases, you can apply this the idea of isotonic regression. You can find the best isotonic approximation. Isotonic meaning just increasing. So of course, when the scores are increasing, you expect the label to be increasing. Okay, so what you can do, you can apply power, have to find this best isotonic approximation. And best here means best in the sense of least squares, in several different senses, but in some natural sense. And power, it works in such a way that all observations become classified into, you can use it as categories. And the base isotonic approximation will be the average label in each equivalence class. Okay, so the power algorithm just gives you automatically these categories. So it's a very reasonable thing to do in the binary case. So it gives you these Venn taxonomies, and it's Venn Abus taxonomy, and it leads, then you apply this Venn prediction machine on top of it, and you get a Venn predictor. Okay, so in the binary case, it's very, it seems to be the best thing to do to me. And of course, the quality of this algorithm it depends on the quality of your initial scoring algorithm, how reasonable it is. But of course, you can't do it efficiently. You can do, and to do it efficiently, you can use this inductive idea. You can split your training set into two parts. But even in this case, the computational efficiency is not obvious because you have to apply this power algorithm. But luckily, it can be implemented efficiently, and I can give you some the time that it takes to implement this idea of inductive Venn Abus predictor. So I call it IVAP abbreviation. So if you're already given the scores of the calibration object or of your calibration set, then the prediction rule can be computed in time O big of k log k. And the main thing here, you need k log k just for sorting. If these scores are already sorted, you only need time O big of k. Just to do calculation just once for your whole training set. And then to apply it for each test object takes time O big of log k. So you can do it efficiently. Okay, so that's very briefly about Venn prediction. And I have even less time about what else can we do under randomness, but it's a topic that I'm interested in at the moment, so I couldn't resist the temptation to include it here. So the difference between randomness and exchangeability. So for infinite sequences, or in practice for potentially infinite sequences, there is no difference. Each exchangeable distribution is a mixture of IID distribution. So this means the difference between these two assumptions, randomness and exchangeability, disappears. It assumes that Z is standard Borel, but of course it's a very weak assumption. But for finite sequences, the difference is very, very significant between randomness and exchangeability. So let me give you just one example, which is irrelevant for prediction, but just to show that these are very different assumptions. So suppose you toss a coin lots of times, 1 million times, and you get exactly 500,000 heads. So it's exactly 50% of heads. And of course, your sequence can be perfectly exchangeable. You shuffle it and you get a perfectly exchangeable sequence, but it's not IID. If you are tossing a coin, you can't get exactly 1/2 of heads. So I computed the probability of it. It's like 0.1%. So that's a small probability. So it shows that the difference exists. So, and there is a discrepancy between our assumption, which is randomness, and what we really need for conformal prediction and event prediction, which is exchangeability. Does it mean that we can achieve much more under randomness? We are underusing our assumption. And I think it's interesting to show that conformal prediction is the best thing you can get. Or if not, to design better ways somehow to use this assumption of randomness better. So, I think the improvement cannot be huge on conformal prediction. The difference between randomness and exchangeability, it can be huge. I'm sure it can be very, very big. But here, when we are doing prediction, so it's very natural to talk about prediction only if the true data sequence, I mean, you have the training sequence, plus your test object, plus the true label. If this true data sequence looks IID. If it doesn't look IID, it's not a problem of prediction, it seems. Maybe it's anomaly detection or it's testing the assumption of randomness, but it's not prediction. For prediction, you assume that in general your process is, your sequence is IID, but when you replace your true test label by something else, you try different ways. Then, of course, you ruin exchangeability. Then you can detect lack of exchangeability. But if it's the true label, you don't expect it to be non-exchangeable or to be non-IID. It should still look IID. So here, I assume that the true data sequence, let me see, the true data sequence Z1 to Zn plus 1, it's IID. And now let's see, can we get something stronger than conformal prediction? So here, it's easier to do it in the language of conformal e-prediction, just because e-values, they're easier to deal with. And then there is so-called, people often call it calibration, but it's a different sense of calibration from the calibration people usually talk about in this workshop. You can calibrate p-values into e-values and e-values into p-values. I think it was James Berger who first started talking about calibration in this sense. He was talking about calibrating p-values into base factors. Okay, so I do it for e-values first, and then we can calibrate them into p-values, and then we can get a result about p-values. Okay, so we have these, we have conformal e-predictors, but we can also use randomness, the assumption of randomness in earnest. So we can consider any randomness e-variable. By randomness e-variable, I just mean a function of all observations of this data, of the data sequence, such that the expected value of this function doesn't exceed 1. So I call it randomness e-predictor, any randomness e-variable. And you can use it as a predictor. How do you use it? So you take this e-variable, and you just plug different different postulated labels for your test objects in it. And you compute the value of this capital E. And you get a prediction function. So it's the best you can get, because here we don't have any restrictions at all on E, apart from it being a randomness e-variable. Okay, so let's check that each randomness e-predictor of this e-variable can be modeled by a conformal e-predictor. But first, let me apply some of the fundamental principles of statistics. So in statistics, you have these principles like sufficiency principle, conditionality principle, and invariance principle. Big three principles of statistics. And two of these principles, sufficiency and invariance, imply that under the assumption of randomness, you should completely ignore the order of your training sequence. It's irrelevant, because you assume randomness. the order is irrelevant. So let me assume it. Let me consider only what I call a train invariant randomness E predictors. Those that don't depend on the order of the training sequence. Okay, so once you are given a randomness E predictor, it turns out you can create a conformal E predictor using it. So the way you do it, you just take the value. When you have some data sequence, you take the value of E on it, and you divide it by the average of E over all permutations of your training sequence. And this way you will get, I call it EX, it will be a conformal predictor. If E is train invariant, randomness E variable. So you can check it, it's easy to check, it's a conformal E predictor. So let's check that this conformal E predictor is almost as good as this original predictor E. So it's almost as good, but there is a caveat here. It's this E to the minus 1. So E here is the base of natural logs, so it's like 2.72. So this number is like 0.37. So here what we are doing, so we need, so here the idea is that we take some B, some Markov kernel, and this Markov kernel, let's talk about the case of classification, and suppose B is just the uniform distribution of all false labels. So we have one label of the test object is true. And let's take the uniform distribution of all false labels, labels which are not the true label. So what we have here, we take the ratio of E to EX. So efficiency means we want E on these false labels to be as large as possible. We want to detect these are not true labels. So when you divide E by EX, you will not get something very small, at least on average. So we take this ratio E over EX on the false labels only. We average it, and then we say that this will be a randomness, it's a randomness E variable. We don't expect it to be large. So the average value of this will be 1. So we are assuming that the true data sequence is random. So the average of this is 1. So we can see the average of this ratio is E or less. So we can beat conformal E prediction at most by a factor of E. And you can't, so this constant E to the minus 1, it's optimal. You can't improve it. And you can, sometimes you can beat conformal predictors by a factor of E. But this happens only when your prediction is extremely confident. When we are talking about E values like n, the size of your training sequence. So it happens rarely. I'm not sure you can exploit it in practice. Using the idea of calibration, you can translate it into the language of a conformal prediction. Okay, so it's I have here some question if it's possible to improve in conformal prediction, conformal E prediction, or is it possible to connect randomness P prediction in terms of p-values and conformal prediction directly? So here I had a detour via E values. Can you get rid of it? So let me now go over some references. So there is my book with courses 2022, second edition of our 2005 book. But there is also a much more recent book by Anastasios Angelopoulos and his courses. So it's just to appear. For conformal E prediction, I have a paper, a recent paper. So there is also a nice forthcoming book by Aditya Ramdas and Rodo Wang on hypothesis testing with E values in general. And also, if you're interested in the last section, so there is there is a working paper. It's a recent working paper by me. But also the idea it goes back to a paper by Ilyana Redinov and other people published in 2003. But it was in terms of the algorithmic theory of randomness, which has unspecified constants, which is not very practical. So I was trying to make it simpler and more practical. Okay, thank you.
Good. We will take a couple of questions. No questions? Yes.
So I have a general question. So, for the great book, so where do you see conformal prediction going? Like, can you make a forecast about the future of conformal prediction? You mentioned a lot about AE value. Yeah, just a general comment.
For me personally, the most interesting direction is relaxing exchangeability or relaxing this assumption of randomness, which I didn't do here at all in this talk. And there is so much recent work which I would love to understand better, how to use it in causal inference, just outside this narrow picture of randomness or exchangeability. E-values, yes, I think it's an interesting topic, but it's just I think it's a useful approach in statistics in general. So it's something that I find counterintuitive and strange, because in the algorithmic theory of randomness, people have been using e-values for ages. It was just one of the definitions of randomness in that sense, like typicalness of sequences under some probability distributions. But in statistics, it wasn't popular outside Bayesian statistics, where they used Bayes factors, but the Bayes factors are still they're different. As an alternative to p-values, it's underused, and I hope it will be used wider, not just in conformal prediction, but in general in statistics, data analysis. It's something I find interesting. Probably that's all I can say about that.
Yes.
I have also one question. Thank you for the nice talk. Is it any connection between Bayesian analysis and conformal prediction? For example, I know one of them is frequency approach and another one is Bayesian, but for example, we are, me and our team in our university, we are working on inverse problems, and especially impossible problems, and of course, Bayesian inference is irreplaceable tool for us. But when we are estimating uncertain quantification, I think conformal prediction is so powerful tool. In that point, can we merge these two different words together as an intersection point to serve uncertain quantification and calibration?
I don't know, but what I find very interesting is something that I already mentioned before. This Bournaev-Wasserman program, so here what you can do, you start from a Bayesian method. You find your perfect predictions, but then you're interested in how sensitive they are to your assumption. Maybe your assumption is too narrow, too special. You want to find out how sensitive they are. So what you do, you can just apply, you can use this conformal machine on top of your Bayesian algorithm. And then if you find that your Bayesian prediction, a research question here is to prove that under the Bayesian assumption, the conformal prediction, the output of conformal prediction is not much worse than what you start from. But then there is one element, I think Larry Wasserman emphasized it, that if you do lose a lot in this, when you conformalize your Bayesian inference, if you do lose a lot, it means maybe your initial analysis was too fragile. You should not trust it anyway, since it doesn't survive well this step of conformalization. So it's probably the only answer I can give now. And these two approaches are very, very different because of their different assumptions. So not all Bayesian statisticians even are willing to test their assumptions. Which is, I know there are different kinds of Bayesian statisticians. A lot of them are happy with testing their assumptions. Some of them are not, like Dennis Lindley, for example. As far as I know, he was just, it's something that you just, you come up, you elicit some personal probabilities, and then you are just using them. All inference should be coming from Bayes' theorem. You should not criticize your initial view, your initial probability distribution. So yes, it's a very different approach, and it's difficult to merge these two. But I think it's great to have these two approaches and see how they can interact and what you can get from them.
Just quickly.
Very quick.
Very quickly, if you have a reference on these last things you said, for example, you said if the conformal approximation, if I'm expressing, is so you mentioned do you have a reference?
Well, it's in our book, in the second 2022 book, which was yes, probably it's not something very well known, and here we talk about it as a research program. And actually, I have a paper on this topic. It's a called 2014 paper. I think it's like 10 years ago. But I have, yes, if you search for it, this Brunei. And it's not a standard term as well. But if you, it's in the index.
You have to recognize it.
Excellent. I think in the interest of getting lunch, we should stop now. So let's thank our speaker again.